Okay, last week we had stopped at this problem. We have this arrangement there of logic gates, and the question says the diagram shows a digital circuit with 2 inputs and 1 output. What describes the action of the circuit? So in other words, all this arrangement here of all these different logic gates is equivalent to which logic gate from the ones that we know? Is it AND, is it NAND, NOR, or OR? We have these options. And we started discussing that by changing the inputs and the outputs, and we saw that it could be, we arrived at the point that it could be either NAND or NOR. And now we need to find a way to distinguish between the two, because we have to have one answer, not 2 answers. And to help us, I wrote already the truth tables of the AND, the OR, the NAND, and the NOR gate, to have them ready so that we don't have to produce them from scratch, to see how we are going to go about here. So I don't know if you remember, but if, for example, if the inputs were both 0 here, if this is 0 and this is 0, just to put our brains in order again, because these are inverters, logical inverters, whatever signal we put here, it will invert it. So zeros here means that it will, the signal will proceed as 1. And here the 0 again as 1 from both of these inverters, and the NOT gate. So the ones will arrive at the AND gates. These two are both AND gates. So one signal, if both inputs are 1, the output will also be 1 here. And so this signal from this top branch will arrive as 1 in the AND gate. And the signal from the bottom input will also arrive as 1, and the output will be 1. So we see if both inputs are 0, the output will be 1. And then if we do the same, if both inputs are 1, if both inputs are 1, let's do it a different color. Sorry, let's change the ones to blue now. So if both of these are 1, if both these are 1 now, the 1 will change to 0, and here all these will be 0 and 0. So what we'll have here, the inputs of the AND gates here will be 0, so the output will be, look at this, if both inputs are 0, the output will be 0. So this will be 0, and this will be 0. The final output is 0. So what we have up to now, if both inputs are 0, the output would be 1. The previous case, if both inputs were 0, the output we found was 1. We see the same applies to both the NAND and the NOR gate. If both inputs here are 1, the output will be 0. So here we see if both inputs are 1, the output is 0, and the same applies again to the NOR gate. So you see, these two cases are the same for both NAND and NOR gates. That is why we had this could be either NAND or NOR gate, or this arrangement here could be equivalent to either NAND or NOR. So in other words, for us to decide which is the correct gate now, is it a NAND or a NOR gate altogether, we have to go to these intermediates to check what happens there. If the one input is 0 and the other is 1, what will happen to the output? So let us clean all this mess here and produce some, see what happens if the two inputs in this diagram are different. The one is 0 and the other one is 1. Let's see what will happen then. So say, for example, this input is 1, I don't know, and the other one is 0. Okay, let's see what will be the output. Now, this one from the top inverter will come out as 0 because it inverts it. Okay, so this will be 0, 0, this will be 0, and this, let's see what happens there. Now, if input 2 is also 0, which means those two are both 0, this will be inverted at the output of this NOT gate. The signal will proceed as 1. So here we'll have 1. In this AND gate, you see the 0 and 1 obviously will be 0. We knew it already because the 1 was the one input of this AND gate was already 0, so we know for sure this will be 0. Now what's happening at this branch? The 0 will change to 1, and here it will be 1 at the when it arrives at this AND gate. But 1 and 0, the output of an AND gate is always 0, because AND gate, both of its inputs have to be 1 for the output to be 1. So here we have 1, 0, 1, the other one, the output is always 1, 0. So what do we see here? That if the input here is 1 and the other input is 0, the output is 0. So let's see here. If for inputs we have 1 and 0, if we have 1 and 0, the output is 0. So you see here, it can't be correct. So this is not an AND gate. This is not an AND gate. But in this case, look at this. If the one of the inputs is 0 and the other is 1, the output is 0. This is correct. So that is why it tells us that our gate, this is equivalent to a NOR gate. So this is the correct answer. The gate, all this arrangement of logic gates is equivalent to a NOR gate. So we had to find it by changing changing combinations here in the two inputs and see what we have in the output. Sorry, guys. Is this understood, or did I say that too fast? If you if you have started studying logic gates, you should be able to do that. Now I hope you followed here what was going on. So if you did, what else do we have here? I wanted us to go to a long paper now and see various questions from the long paper, because there are a couple of questions here, but it's nothing really too special. Let us go to a long paper and from a past exam. Actually, this is from March 19 from this year. This paper, this is the last question. We'll go backwards from the last question and we'll move forwards. Okay, let me find my paper now. This is, we said, question number 11. Okay. There is the question number 11. It's from radioactivity. Okay. Let's change the color. Let's make it red. Okay. So one isotope of iridium-194 is represented by this representation. Okay. This isotope decays by beta emission to a stable isotope of platinum. All right. Complete the Nuclide equation for this decay. So we need to complete this beta decay of iridium-194. We just need to add the numbers. Now, this isotope decays by beta emission. All right. We assume that this beta emission, they mean the electron. This is an electron that is emitted. And how can we symbolize the electron? What numbers can we give it so that we can make our lives easier with the conservation of charge and the conservation of nucleons? So because the electron, we assume it has a charge of -1 and a mass of 0 because it's not a nucleon. So this is what we can do here. So here we can place the numbers -1 and 0. And for platinum now, what can be the numbers, the atomic number and the nucleon number for platinum, this daughter that is produced? Remember that since the charge is conserved, the charge on the left hand side is 77. So 77 must be equal to the sum of the charges of the product, which is this daughter of platinum, which is an X. We don't know, we need to find it. And this is minus 1. So X minus 1 should give us 77. So what can be the X here? It is 77 plus 1, which is 78. So this should be 78. I forgot to bring my periodic table. Anyway, if we look in the periodic table, we'll see that the platinum has an atomic number 78 in any case. But we can calculate it and we can find it this way. So this number, which is the atomic number for platinum, is 78. Now, to find the Nucleon number of platinum, 194, which is the Nucleon number on the left-hand side, has to be conserved, and which means this must be equal to this, the Nucleon number of platinum, which we don't know, let's call it Y, plus 0, because the nuclear number of the electron, which is emitted, is 0. So the Y, in other words, is 194. So this is the answer up there. We must place 194. So these are the missing numbers, and this is our answer. Okay. So we need to apply the laws of conservation of nucleons and the law of conservation of charge and find those unknown numbers. And we also need to know how to symbolize, to represent the beta particle emitted. All right. Now the next question says, the half-life of iridium-194 is 19 hours. So the half-life of this iridium-194 is 19 hours. Now, a sample of iridium-194 has an initial count rate of 1,100 counts per minute. Okay, calculate the count rate from this sample after 38 hours. Okay, after this time, after 38 hours, and we know that its half-life is 19 hours. 19 hours is the half-life. And already we can see that 38 is double the 19. It's 19. Okay, so 38 hours is double 9. In other words, 38 hours corresponds to 2 half-lives, because if we can't see it, you could just divide it to make sure. This is 2, means 2 half-lives. Okay, calculate the count rate from this sample after 38 hours. Okay. Initially, the count rate was 1,100. 1,100 was the count rate. That was the initial count rate. After 1 half-life, this will give us half the count, isn't it, per minute? So what is half of 1,100 is 550 counts per minute after 1 half-life. And after a second half-life, because we have 2 half-lives here, and half of that is 275, isn't it? 275 counts per minute. So this is after the first half-life, and this is after the second half-life. So the count rate after 2 half-lives is 275 counts per minute. So this is our answer after 2 half-lives, after 38 hours, in other words. And we can also work this differently, in a different way. Actually, which page is this in the book? Page 326. 326 in the book. They have this worked examples 23.1, and they tell you, they also show another way to calculate what happens after so many half-lives, which is we can use the formula, in other words, that the initial activity, we can place the initial activity, if we know the initial activity, divide by 2 to the power of n in general, where n is the number of half-lives that have elapsed in a problem. So in our case, the initial activity is 1,100 counts per minute, 1,100 counts per minute. And what do we place here? What is the n in our case? It's 2 half-lives, because 38 hours corresponds to 2 half-lives. So we have to divide with 2 to the power of 2. Remember, this n in our case is 2 half-lives. And therefore, this is 1,100 divided by 2 to the power of 2 is 4. And we get the same answer, 275 counts per minute. So this is another way to calculate the count rate after a certain period of time, if we can find out to how many half-lives this period of time corresponds to. So this is the formula that we can use if we don't want to do it in this way. Because sometimes, you know, we may have many half-lives and we cannot keep on dividing and dividing by 2. So we just go straight to this formula, and we found the count rate per minute, or count rate after so many half-lives. Okay. All right. So, okay, we finished with this question. Here is our answer. Now it says here, state 2 ways in which gamma emission differs from beta emission. Yeah. Well, what are gamma rays? We need to remind ourselves what gamma rays are. These are gamma rays are just electromagnetic radiation. They are not particles. They have 0 mass. So what can we say? For example, gamma rays, let's say gamma rays. What are characteristics of gamma rays which are different from the beta particles? Because remember, these are electrons, the beta emission. Well, gamma rays, we can say that is electromagnetic radiation, whereas beta emission is particles. These are particles, in fact, electrons, where this one is just radiation. What else what is different? The gamma rays have no charge, whereas the beta particles have a negative charge. This is an important difference. These ones are charged because they're electrons charged. What other difference? We can say that this very penetrating, and they can go through a big thickness of lead. We can say very penetrating radiation, penetrating, whereas the beta particles, being electrons, can be stopped by 2-3 millimeters, say 3 millimeters of some metal like aluminum. What else can we say? They have, the gamma rays have no mass, even if we consider them as photons, still no mass, whereas the electrons do have mass, have a mass. We can say that these are not deflected by electric and magnetic fields, no deflection in fields, by fields, where the beta particles, being electron and having charge, are deflected by electric and magnetic fields, and so on. I mean, any 2 of these kind of differences will be fine. There are more. State 2 ways in which 2 ways. Any 2 differences from all this will be enough. Okay, so we need to know what gamma rays are and what beta particles are, so that we can explain their differences. Okay, this question is finished now. It was all for 7 marks. Let's see, 7 marks. What was the previous question? Let's see. It's about, I see transformers here. Question number 10, sorry. Paperwork here. The electrical energy produced by a power station is transformed over long distances at a very, is transmitted over long distances at a very high voltage. Yes. So the electrical energy is transmitted over long distances at a very high voltage. Explain why a very high voltage is used. This is a very, very important question, and we need to know very well, why do we transmit electricity at such huge high voltages over long distances and not at small voltages? Because by transmitting it at very high voltages and by using transformers, we can reduce the current. So this is a very, very important reason to reduce the current. If we transmit it at high voltages, means that the current that we use, the current then can becomes low. The current is low, and therefore, if the current is low, the wires don't heat up a lot or heat up very little, which means we decrease the loss of energy to the surroundings by heating. So the current is low, therefore the energy loss is reduced. Energy loss is reduced. Very important factor. Or else all the energy, if the current was high, if we were transmitting electricity at high current, the wires would be so heated up and warm the surroundings, and all the power that we transmit would be lost to the surroundings rather than arriving to the cities that where we need it. So the energy loss is from heating is reduced considerably, which means now also with a low current we can also use thinner wires which have a lower, so they can have a higher resistance, but since the current is very low, we don't energy is not lost. Thinner wires, we can use thinner wires which cost less, or we which means the cost is reduced. And also, if the current is low, we can even the wires are also lighter. The wires can be lighter. They are not very heavy. Wires are lighter by making them thinner, lighter, which means that they don't need so much support anymore. Less support, in other words, can have less pylons, in other words, to support them. Less support, which means again less cost. So you see there are very serious consequences of using low current. Another thing that we can say is that instead of copper wires, which are expensive, we can use aluminum wires, which are much cheaper. Although aluminum is not as good, copper has less resistance than aluminum, but aluminum is, because it's so much lighter and cheaper, again we reduce the cost of transporting it through wires and also through the support, and again we end up in the less cost. I mean, cost is a very important factor on what type of wires we use, because it's not a joke. I mean, having to transmit the electricity through kilometers from the power station to the cities. So this is an important factor. So you see, by reducing the current, by transmitting the electricity at high voltage, low current, there is a lot of gain. We decrease considerably the loss of energy, and also we decrease considerably the cost of all these cables and pylons and, that we need to transport it. So these are very important factors that we need to be very well aware of that so that we can answer such questions. Okay. Now, by the way, how do we, it's not the question does not ask how we decrease the current, but remember that the power is it's voltage times current in general, isn't it? So by increasing the voltage, the current, and decreasing the current, we send the same power. But how do we do that? Actually, we do that by using transformers. The transformers can do these transformations. And here we have a transformer. It says now the figure represents a transformer. Here is the primary, here is the secondary, and we can see the secondary has less windings, which means it's a step down transformer, this one. Anyway, let's see what the question says. The primary coil has 4,000 turns. Okay, so these are 4,000 turns, and an input of 120 volts. So here is our input voltage. The secondary coil has an output of 9 volts. Okay, they give us the output, they don't tell us how many turns. Calculate the number of turns in the secondary coil, as we would expect it, because they don't give us the number of turns. All right, so what is the transformer equation that we can use. The voltage of the primary over the voltage of the secondary is equal to the turns in the primary and the turns in the secondary. We can use it straight away. We know this, we know this, we know the windings in the primary. We can find this is our unknown. So from there, if we solve for the secondary turns, the turns of the secondary coil, okay, what do we have? So these two multiplied voltage of secondary times the turns in the primary divided by the voltage in the primary. In other words, I solved this equation for this unknown. And what do we have here? Voltage in secondary. Voltage in secondary is 9 volts. And the turns in the primary are 4,000 times 4,000 divided by the voltage in the primary, which is 120 volts. And so this is 9 times 4,000 divided by 120. We get 300 turns. So these are the turns in the, so these turns are 300 turns. Okay. So here is our answer, yeah. Now the next says, state a suitable material for the core of the transformer. Well, it has to be soft iron at best. Well, soft iron, we can say, or just, even if you say iron, they will consider it as correct. Okay. Soft iron is, of course, the best because the current in the primary is alternating current, of course, and keeps on alternating. So the magnetization of the coil has to change very easily. That is why the best is to use soft iron. Soft, obviously, it's in a magnetic sense, and not soft like in the sense of the mechanical properties. It's magnetically soft. It's easy to change its magnetism. All right. So that is the end. Oh, goodness, it's 11:59. Right. Guys, do you have questions? I think next week let us continue with this exam paper. Let's do all the questions from the exam paper from the first to the last one, including mechanics and kinematics. And I think from now on for this last month of November and a bit of December that we have, maybe we should start doing all the questions from past exam papers in a way that we review all the topics at once, and we also see how they appear in exams. And guys, if you have any questions, and if you want us to talk about particularly about the topic, I can arrange a live lesson for this particular topic, maybe more than one lesson. The one that you think you need more clarity or something. Okay, you feel free to tell me what you want us to do. Okay, all right. So now we have to now to say goodbye, and guys, enjoy your week. All right. And remember, you can always tell me what you want us to do here.